Okay, so thank you very much, Professor, for your kind introduction and also your invitation. I'm very honored to be here to give the presentation. As you said, today I'm going to show you basically a part of my PhD project, which is the high-fidelity numerical investigation of a hydrogen air rotating detonation combustor. My talk will basically be divided in two parts. After a brief introduction to RDCs and also the test case I'm going to analyze, I will focus firstly on numerical models, so the main choices we did to model the combustor, and then I focus, of course, on the results of the simulation, and specifically I'll focus on the reactants and refill and mixing inside the rotating detonation combustor. And finally, this will lead me to the conclusion of my talk. As you probably already know, when you are talking about rotating detonation combustion, we are talking about pressure gain combustion. That we mean all the families of physical processes which allow a total pressure increase during the combustion cycle, which is happening in a fixed volume combustion chamber. These processes are of great interest because they allow a significant increase of ideal cycle efficiency with respect, for instance, to traditional thermodynamic cycles like the Brayton cycle, or also the Humphrey cycle, which is a constant volume cycle combustion. The pressure gain combustion comes in a lot of different implementations and can exploit both the deflagration regime and also the deflagration regime, but they all share the very intense and steady operation of the complete device. Among these devices, probably the most interesting are the rotating detonation combustor, because they are not only very promising for propulsion, but also for gas turbine integration. This is due basically because their design is quite simple. They don't have moving parts, and also the frequency they work is very high, and this is kind of mitigating the fluctuations which reach an eventual downstream turbine. In a rotating detonation combustion, in case someone is not familiar with this technology, we have typically an annular combustion chamber which is fed by the base with reactants, and then they are burnt by a detonation wave which is propagating inside the combustion chamber in a azimuthal direction, so is continuously rotating inside this combustion chamber. And of course, then we have the hot gases which are exiting the combustion chamber at very high total pressure. One of the most critical aspects maybe in rotating detonation combustors are the injector design. This is because, of course, this drives the reactants refill and also the mixing inside the combustion chamber, which in turn drives the mixture reactivity and also the wave stability, so is able to discern between a chaotic propagation of the wave and a regular pattern of wave, which is of course what we want inside this combustor device. Here on the right, I reported just some examples of the huge variety of different injectors configurations, which are very, as you see, different, but because they have to attain conflicting requirements. Basically, they have to give a fast and very uniform mixing of the reactants inside the combustion chamber, but at the same time, they have to decouple the pressure of the combustion chamber from the pressure inside the feeding plenum, and so they should have a very high delta P sub P, so a very high pressure loss across the injector. On the other hand, if we have a very high total pressure loss across the injectors, we will lose a lot of pressure gain, and this is also one of the most critical part of achieving a positive pressure gain in these devices, because a lot of pressure is lost across the injector. The injector design is also more complex because it's not only to be designed in a fixed condition, but it has to be designed in a transient condition, because its functioning is really coupled with the detonation wave inside the combustion chamber. And so this makes really, really hard to be studied experimentally. I mean, it's very, very hard to study experimentally the reactants mixing in reactive condition in a rotating detonation combustor. To this reason, we set up during my PhD a collaboration with U Berlin, and specifically with the Professor Miles Bohn group, which is performing experiments on a laboratory RDC. And our task, and particularly my task, was the development of a high-fidelity numerical model of the rotating detonation combustor, specifically going to investigate the reactants refill and mixing inside the combustion chamber. The TU Berlin rotating detonation combustor is reported here in this slide. In a section, you can see that is a non-premixed hydrogen air rotating detonation combustor, where we have the injection of hydrogen through a number of discrete injector at the base of the combustion chamber in axial direction. And then we have a slot of air which is injecting the oxidant through the outer wall of the chamber, realizing so a jetting cross-flow mixing configuration of the reactants. The combustion chamber is a simple straight-walled annular combustion chamber, which is open to the atmosphere. So we don't have pressurization of the system, but also we don't have a cooling system of the combustor. So the operation is typically limited to a few seconds of operation. This combustor has been designed to be modular, so we have possibility to change the plate for deciding the height of the air slot, the number of injectors of fuel, but also there is a possibility to add eventual outlet restriction at the end of the combustion chamber. In our specific case, we decided to test a configuration without any outlet restriction and with 100 0.5 millimeter of diameter fuel injectors at the bottom of the combustion chamber, while the air gap height, so this height was 1.2 millimeters tall. On the right, you can also see the instrument, the test rig. Basically, it's heavily instrumented, but the majority of the probes are pressure probes. So we have piezoelectric probes, capillary attenuated pressure probes, and keel probes at the outlet of the combustion chamber. They have also a high-speed camera, which is recording the visible light emission from the outlet of the combustion chamber. And so this is the test rig in TU Berlin. For our analysis, we decided to study a stoichiometric test point. So we have the nominal mass flow rates of air and fuel, which are in a stoichiometric ratio, and the flow rate inside the combustion chamber is relatively high for the capabilities of the test rig. So it's 290 kilograms per square meters second. In these specific conditions, because of course this combustor has many other design, has the possibility to operate in different wave modes. But in this specific condition, we have a clear single wave propagation. So a single wave which is moving inside the combustor, which is rotating at 6.3 kilohertz of frequency inside the annulus. Again, in this specific configuration, we have for different reasons, which I show here in this very interesting map from the guys of Miles group. We have a lot of total pressure losses across the injector, so we don't have a positive pressure gain across the combustor. Specifically, in these plots, we can see the measured pressure gain as a function of the mass flow rate on the x-axis for different air injector areas and also for different outlet areas. where the line or the yellow line is the unrestricted outlet, so our configuration. Our test point is the start, so as you can see, is one of the most penalizing configuration for the pressure gain, basically because we have the very small injector area, which is losing a lot of total pressure across the injector of the oxidizer. And also the outlet area is unrestricted, so is not increasing the pressure inside the combustion chamber. In this condition, so we have a negative total pressure gain, so a total pressure loss of 58%. So when we decided to study this rotating detonation combustor, we have some key features of the model to be properly addressed, and which are summarized here in this slide. First of all, of course, we are dealing with supersonic combustion, but also we are dealing with turbulence. So what we needed was a fully compressible Navier-Stokes equation solver with a proper treatment of turbulence. So we decided to use the AVBP code, which is developed by Serfax, using a large eddy simulation with the Weyl subgrid closure and the wall functions to model the boundary layer near the walls. Another very key point of our model was the complete inclusion of the injection system. As you can see here in this section of the computational mesh, we decided to include the complete planar of hydrogen and air, and also, of course, the feeding ducts of the reactants. And this is very critical because, as I was saying at the beginning, the injector's operation is strictly linked to the pressure inside the combustion chamber. So to properly solve the interaction between the wave and the injector, we need to explicitly solve the pressure feedback in the injector channels. This allowed us also to impose directly the pressure, which are measured experimentally at the two different feeding plana. And specifically, we are using a Navier-Stokes characteristic boundary condition, both at the inlet, but also at the outlet, where you can see here, the domain is not cut. This is the actual domain, so we don't use an outlet plenum, but we directly impose the static pressure, the atmospheric pressure at the outlet, because this boundary condition, the Navier-Stokes characteristic boundary condition implemented in the code, is able to switch between locally supersonic and subsonic condition depending on the local Mach number, and so we can get a proper boundary condition without spurious effect on the flow field, even without a discharge plenum. We decided to discretize the complete domain in 178 million of pure tetrahedral elements, and this is a section of the mesh where, of course, you can see also the sizing of the elements, and when we adopted the specific refinements near the injection, and particularly in the region where we expect the formation of shocks due to the supersonic injection of both the fuel and the air. The other two critical parts for the model, which I will show you in the next two slides, is also that we need a combustion model which is suitable for detonation, but also which is suitable for a CFD simulation, which can be very expensive in terms of computational requirements. And the last point is also a fast and a very effective initiation strategy of the detonation wave, which is not so easy to achieve in a computational model. And so I spent a lot of my efforts to develop this specific initial solution for the detonation. Our numerical method is summarized very briefly here in the bottom of the slide. Basically, we are integrating in time with an explicit an explicit algorithm imposing the maximum CFL number inside domain of 0.7, and this is giving a time step which is around 6 nanoseconds inside the simulation. We're also using localized artificial diffusivity or LAD for stabilize the simulation, but also for capturing the shocks inside the domain and stabilize the possible numerical fluctuation or wiggles we can develop in case of supersonic structures. As I was saying, one of the most critical part is having a combustion model which is suitable for safety simulation, and we decided to design a global mechanism named 4S1R, so 4 species 1 single step scheme, which is reported here. Of course, very simple global scheme for the oxidation of hydrogen, which allows us to model also the mixing and the fusion of the reactants, because inside the code we are specifying the Schmidt number of each species. In our model, we are not accounting for the subgrid turbulence and combustion interaction, because in the literature there is not still, and also in our experience, it's still not so clear the interaction between a turbulent combustion model and the detonation front. So we decided not to use at all the turbulence combustion interaction. As I was saying, this global scheme was developed specifically for the condition that we are interested in. Specifically, it was calibrated for near atmospheric hydrogen air detonation, calibrating the thermodynamic parameters and also the kinetic parameters with different targets. Thermodynamic parameters were chosen to target the TJ speed over a wide range of equivalence ratios. And as you can see here, the scheme is performing very well in a very wide range of equivalence ratio in terms of CJ speed, but also in post-shock and equilibrium and the CJ state in all the range of equivalence ratio. We performed basically a slightly adjustment of the formation enthalpy of the water to achieve this agreement with a detailed scheme. We also tested what happened if we went outside the design point. So in these maps, you can see the comparison between our scheme and detailed scheme in terms of different temperature and pressure of the fresh gas. You can see that even if we move away from the design point, which is stoichiometric, 300 Kelvin, 1 bar, and we stay between 1.5 bar and 350 Kelvin, which is more or less the range of condition we expect in the refill region inside the combustor. We can see that the TJ speed is well captured by our numerical our combustion model. Concerning the kinetic parameters, we decided to target the pre-exponential constant in the activation energy to match the half reaction thickness around the equivalence ratio 1. And we did this by solving one-dimensional detonation profiles in Cantera. Here you can see the comparison between the one step and a detailed scheme, which is one by Boven. Of course, as you can see here, also in these profiles, we have a one-step scheme. So it's a global scheme. Of course, has its limits. Specifically, the main limits of our combustion model is that the half reaction thickness is overestimated if we have a composition which are very far from equivalence ratio 1. And also the deflagration speed is underestimated for any composition. And this is because we decided to focus our combustion model on detonation regime and not on deflagration speed. And of course, this was a preliminary evaluation made in Cantera, but still we don't have any information about the performances of deflagration speed of our combustion model in the specific computational mesh that we are using in our simulation. The last key feature of the numerical model that we faced was the initiation of the detonation wave inside the combustor. This is very critical because first of all, we have as soon as we ignite, so we initiate the detonation process, we need the injectors to be fully initialized, and so they be basically ready to inject fresh reactants inside the combustion chamber as soon as the detonation wave propagates during this really first revolution inside the combustion chamber. So what we did is we ran a simulation with a preliminary no-reactive flow of about 2.5 milliseconds, which is around the 7 flow-through time of the combustion chamber of our test rig to fully initialize the injectors. And then we cut the cold flow solution about 6 millimeters inside the combustion chamber, leaving unaltered the solution below 6 millimeters. So here you can see the cold flow solution at the bottom, and at the top we superimpose a gassed RDC flow field. This gas RDC flow field is built around the one-dimensional detonation profiles, which is calculated with the Cantera in overdriven state is 110% of the TJ speed in hydrogen air stoichiometric conditions, and then we built the solution around this profile. So basically, the detonation profile is here, and which is then followed by an expansion fan where you basically expand the pressure from the TJ pressure to the atmospheric pressure, which is set in the combustion chamber, which is also the outlet pressure. And we then calculate accordingly the temperature as an isentropic expansion following this pressure. Here on the right, you can see the pressure field and also the hydrogen mass fraction field inside our combustion chamber. We then put a linear refill region, which is the blue in this temperature contour, but also the yellow part in this plot, which is filled with premixed reactants, so hydrogen air in atmospheric composition, in stoichiometric composition, while all the other parts of the combustion chamber are filled with equilibrium products, so TJ products, static, and at the pressure at the outlet. Okay, so now let's look at the simulation results. First of all, I will dive into the really first instance of after the initialization. Here on the left, you can see different probes. This is a pressure probe inside the combustion chamber as a function of the time, and the inlet mass flow rate of the air, the fuel, and the resulting equivalence ratio inside the combustion chamber. Here on the right, you can see the unrolled constant span section at 25% of the span and 75% of the span in terms of temperature and hydrogen mass fraction. Let's see what happens right after the desalinization. Here you can see that we have immediately, I would say, right after 1 or 2 revolution of the combustion wave, we have really fast stabilization of the combustion process. And from the diagrams on the left, you can see that only after 6 revolution of the wave, the inlet mass flow rate has stabilized, and so the combustor assumes its, I would say, stable propagation, where the flow fields are showing the typical flow field of a rotating detonation combustor with the refill region, which is more or less a linear detonation front, the oblique shock in the other part of the combustion chamber. And this happens both at low span and also high span. Of course, also here you can see that there is a quite significant variation between low span regions and high span regions. But this is a point which I will explain in more detail in the next slides. Before looking at results, it's very important that any numerical model is validated against experimental results. So we did a comparison of our model to any measurements we have for this specific condition. We have, of course, the single wave mode, which is matched in our simulation, as you were seeing in the previous videos. And then we compared the rotation frequency inside the combustion chamber of the way by post-processing pressure probes inside the combustion chamber. Our combustion system propagates at 7.5 kilohertz of frequency, which is against the 6.3 kilohertz measured during the experiments. So we are overestimating of about 20% the detonation speed inside the combustion chamber. This is probably due to uncertainties in our model, which is the use of adiabatic walls, while in the reality, of course, the walls are not adiabatic, and also the very short duration of the test is also associated to very strong thermal transient of the walls of the combustor. But also, as I was saying before, in the combustion model, we are also underestimating the deflagration speed. So this again could be a possible cause of our overestimation of the model. However, if you consider the pressure inside the combustor in terms of outlet total pressure, comparing our total pressure in the outlet with the Pier probe in terms of mean and also RMS at the outlet measured experimentally, we can see that we have a very good agreement in terms of outlet pressure, but also we have a very good agreement in terms of pressure axial distribution along the outer wall, which is measured experimentally using CTAP. As you can see here, we are slightly overestimating this value with respect to the experiments, but this is kind of expected because the experimental measurements with the CTAP is capillary attenuated pressure sensors are very long tubes, so the pressure waves inside these tubes is for sure attenuated with respect to a probe which is positioned at the right in the outer wall as in the simulation. Overall, if we consider the comparison to experiments, we can see that the model is overall aligned with the experiments, allow us to do some post-processes and also complement the experiments, providing additional information. For instance, as I was saying at the beginning of the presentation, one of the most interesting parts which we want to clarify is the study of the fresh mixture, which is developing inside the refill region, because of course this is very hard to be investigated experimentally, but it has a very huge impact on the wave strength and stability. But also there is also a specific drawback in this specific system. As you can see here, this is the hydrogen mass fraction. We have, this is of course the steady flow field. This is the average inside the reference frame of the detonation wave. And as you can see here, right after the oblique shock in the slip line, we can see a very consistent mass of hydrogen which is exiting the combustion chamber. This is of course a characteristic which is not desired in a combustion system, because we are wasting hydrogen mass fraction which is not burnt, but it's exiting the combustion chamber. Here, as you can see, the colors are placed like the red is rich, the white is stoichiometric, and the blue is lean condition when hydrogen is mixed with air. And in this condition, we can see that specifically we have a rich pocket of mixture which is at the top of the region, and so it's not possible to burn completely this gas because there is no enough oxidant in this part. This, of course, is a situation which is very critical in a system where the residence time inside the combustion chamber is very small. So what we want to do is to provide a complete characterization of the fresh mixture inside the refill region, but specifically we want to know the gas state in a plane which is right in front of detonation front. So this is really the gas which is then detonating, so which is invested by the detonation front. This gas, as you can see here, has an axial and radial variation, but is also a tangential or temporal, if you want, variation, because this frontal plane is preceding the detonation front continuously during the detonation. And so we have the subsection of the different discrete fuel injectors here, which are giving this periodic fluctuation between a position where we have the fuel jet and where we don't have the fuel jet. So we have a real three-dimensional variation of these of the gas in this plane. So what we did to study this gas was sampling the gas state in this frontal plane during a complete revolution with a very high frequency. This is specifically 31 megahertz, which is corresponding to 30 samples about per injector's pitch. And we are sampling the gas state in this line, which is this blue line, consistently 10 degrees ahead of the front. In parallel, then I will show you later the results. We are also tracking the detonation front surface so that we can place our plane, our sampling plane 10 degrees after the barycenter of our detonation front. If we take the average of the gas state in this line across one complete revolution of the wave inside the combustion chamber, we can get temporal statistics, and specifically in this slide, we have reported the time average quantities inside the plane, focusing on the radial and axial distribution. So we are looking at this plane here. As you can see here, of course, we have a radially inward injection of air and the fuel which is injected here. So we have the impingement of the reactants on the inner wall in a very fast region of the flow, while on the outer half of the combustion chamber, we have very slow fluid, which is also associated to a recirculation region right above the air gap. This region, if we see, for instance, the water mass fraction, or also the temperature, is associated to a hot products accumulation, and also hot temperatures in this region, which are settling because of the flow field. As you can see clearly from the water mass fraction, we have an efficient refill only of the inner half of the combustion chamber, basically, because in the outer half of the combustion chamber, we don't have an efficient injection of the reactants, or in other words, we don't have a displacement of the products toward the exit of the combustion chamber. And as a result, this will lead to parasitic combustion losses in all this range. But what is also very interesting is that if you look at the hydrogen mass fraction in the inner half of the combustion chamber here, again, here the color map is made so that the blue is lean condition, the white is stoichiometric, and the red is rich condition. And you can see here we have a different condition of the mixture, which is rich at the top, lean at the middle, and of course each are unmixed reactants at the bottom of the combustion chamber. So we have a considerable axial stratification of the mixture inside our refill region. This is very interesting to be analyzed because it's fundamentally linked to the differential blockage of the hydrogen and air injectors. If we consider here, we have a section of the combustion chamber at the injectors where we are plotting the air mass flow rate, the blue line, and the fuel mass flow rate in each point of the injectors. with respect to the detonation front. As we can see here, the fuel, so the red line, is basically unaffected or has a very minor impact of the detonation wave, so it's injecting fuel for a whole the period of the revolution. On the other hand, the hair is very differently affected, so we have a very huge blockage of the hair injector. Of course, this is due to the different geometries of the injectors, but this is also leading to very high imbalances of fuel and air ratio. So if we calculate the hair to fuel ratio deriving from these two different mass flow rates, we can see that in the first 90 degrees behind the wave, we have mostly a rich mixture which is entering the chamber, which is then convected upstream and settling at the top of the free region. Then we have in the other 100 degrees after a mostly lean mixture, which is the mixture which is present in the middle of the refill height. And at the end, we should have a roughly stoichiometric mixture in the last 90 degrees, but of course in the last 90 degrees reactants don't have the time to mix. So this mixture, we can say that overall should be stoichiometric, but of course the spatial dishomogeneities are preventing us from seeing a stoichiometric, so a white color in this region. So what's very important is that this is also observed in other studies. We can also remark here the injector dynamics is very, very important, and is also maybe more important than the injection of the injectors at full load, so unperturbed injectors. This is because if we are able to tailor or control the dynamics, so the transient dynamics of the injector, we are also able to drive the axial stratification of the mixture, which is in this case the worst case possible, because this, if you remember, this rich mixture at the top is partially unburnt, so it's exiting the combustion chamber and reducing the fuel efficiency. However, if we would be able to, for instance, have a lean mixture at the top, or a pure air at the top, we should avoid all these fuel inefficiencies inside the combustion system. The other part that we are interested in is the tangential or temporal variation. So if you remember, this plane is moving in this direction, so it's preceding the detonation front, and so it's facing this periodic variation of the gas state. This is again hydrogen mass fraction. As we know, the periodic fluctuation of this gas, we know the frequency. We can do a phase locked ensemble average of our fields, which are reported here on the right in terms of hydrogen mass fraction as a function of the injector phase. In other words, this is the average of all the samples which are aligned with the fuel injector, while this 50% is the average of all the samples of the gas state in between two fuel injectors. And then, of course, we have all the other intermediate conditions. As we expect, of course, we have a variation of the gas properties of the phase locked properties as a function of the fuel phase at the bottom of the combustion chamber, where is unavoidable because we have this fluctuation. But above 8 millimeters inside the combustion chamber, we still don't have any variation with the fuel injector. So in other words, when this plane rotates inside the combustion chamber, doesn't see any variation in average terms above 10 millimeters of the mixture state. And this is very interesting because when we have the gas state in the frontal plane, we are also able to calculate the local CJ speed, which is a thermochemical parameter, which show us how the wave should be propagating in that specific mixture, considering the hypothesis behind the CJ theory. Specifically, we can calculate with the CJ speed as a function of the local temperature, pressure, and composition, and then we calculate these time varying maps, which again we can post-process with phase locked ensemble average in terms, in this case, of CJ Mach number in the fresh gas, and this is what you see here on the right. We have again the same behavior as the hydrogen mass fraction in these maps, because the CJ speed is mostly depending on the composition of the mixture. So where we have a flammable mixture, we have a non-negligible CJ speed in this region, while here in between two fuel injector, where we have only air, of course, we don't have the CJ speed. But again, above 10 millimeters inside the combustion chamber, the CJ speed associated to the mixture inside the refill region is basically constant. It's not a function of the normalized phase with the injectors. However, we still would like to characterize what's the impact of this fluctuation of CJ speed on the real detonation wave, which is propagating inside the combustion chamber. So we want to know if this periodic variation is leading to periodic fluctuation of the detonation front inside the combustion chamber. And so what we did is develop a strategy for dynamically tracking the detonation front inside the combustion chamber, which is basically based on a selection of a pressure isosurface inside the combustor and sampling this isosurface at 8 megahertz of frequency. We then process this, and we did this directly in AVVP. We then wrote a dedicated Python script to process this isosurface, so identifying the leading points on the surface with a half overlapping moving windows, which allow us to discriminate between the points we don't need and the actual leading front points, the red points on the isosurface of pressure. This is the side view of the detonation front, which is propagating inside the annulus. And with this procedure, we get everything we need. So we have a discrete function of theta as a function of the radial position, the axial position, and the time, which is actually what we are seeing here in this plot. Of course, we can, for instance, calculate the time average of the front elevation with respect to its average angular position, which is what you see here on this contour. And for instance, we can see that we have this peculiar protrusion of the front in this region, which was the circulation region where the sound speed is higher. And again, this is what also is observed in other detonation studies, where we have this protrusion of the front in regions where the sound speed is higher, so the expansion waves are faster than in the other regions. By the way, once we have once we have the time varying function of the front, we can calculate the leading shock speed. So basically, we are doing the hypothesis that the front is moving normally to itself, and we can calculate the displacement speed of this front. And this is what you see here on this plot. Of course, the region of the protrusion is very fragmented, so it's subject to high fluctuation, which is not really accurate. So we decided to mask this part. But here you can see the instantaneous and local fluctuation of detonation speed of the front while the wave is moving inside the annulus. We can take again the time average, and we had to expect, of course, if we smooth out also all the local fluctuation of detonation front, the detonation front on the outer wall must be faster than the front on the inner wall, because it has to run a longer path than the inner wall. But what is very interesting is that if we take the ratio between the local detonation speed and the GJ speed that we calculated in the frontal plane, and then take the average, we can see that this speed is aligned to the GJ speed in the inner part of the combustion chamber, which is slightly underdriven. It's about 5% underdriven, while we have a considerable overdriven level in the outer wall. It's about 10% of overdrive level on the outer wall. This is very clear here in this plot. If we only do the axial leverage in this part of the front, which is the stable part of the front, we can see that the red line is the CJ speed of the mixture. The black line is the actual speed of the front. We can see that in this region, so below 50% of the span, we have a good agreement between the two, while the discrepancy is higher, so we have an overdriven propagation around the outer wall. This leads us to say that the propagation of the front is driven both by the mixture state and the curvature, because in the inner wall we have an agreement between the speed of the front and the speed that the front should propagate, so the CJ speed, while at high span we don't have this agreement with the CJ speed, while this high speed and the outer wall is only due to the curvature of the front. Finally, we can finally answer the question I was asking before. So if you remember, we have this fluctuation, tangential fluctuation due to the periodic occurrence of fuel injectors. So we have at the bottom hydrogen mass fraction and air, which are of course fluctuating, and this is determining also variation in the local CJ speed of the mixture. So we would like to see if the front is showing preferential speed drop in correspondence of the presence of the injector. So what we did is to calculate the two-dimensional probability density function as a function of the injector space, the injector phase, sorry. And we did this in different zones. So we have this map, which is at the bottom of the combustion chamber, and these two maps, which are in the top part of the detonation front. And here we can see that basically the detonation speed, so the PDF, the detonation speed is distributed roughly around the local CJ speed in the regions 1 and 2, without any preferential fluctuation, so speed drop as a function of the injector phase, while we have a preferential drop of speed only at the base of the chamber. Again, this is showing that the speed also at the bottom of the combustion chamber is mainly moving at the TJ speed, but we have a preferential fluctuation of the detonation speed right after the position, which is corresponding to 0.5 in the phase of the injector, which in other words means that right after the position in between two injectors, the detonation front is showing periodically a reduction of speed. However, again, this is a local behavior which is not affecting the other parts of the domain. So we can say that basically these fluctuations are only limited to the bottom of the combustion chamber. So went a little bit long, sorry for that. It's seen that I've shown you that we developed the LES numerical model of the tube burning RDC, trying to characterize the fresh mixture, which is refilling the combustion chamber. This fresh mixture is showing large dishomogeneities both in the radial and the axial direction. And specifically, the axial stratification of the mixture is due to the differential blockage of the air and fuel injector dynamics. And finally, we see also that with the density of the injectors of the fuel that we have in this specific configuration, the fluctuation of the detonation wave are only confined at the bottom of the combustion chamber, while is not showing a global fluctuation in phase with the combustion, in phase with the injector fluctuations. So that's it. I thank you very much for your attention, and if you have questions, I'm happy to answer.
Okay. Yeah, thank you very much, Pier, Carlo. This is very interesting presentation, and also this. I guess this is quite the rigorous calculations you did with all this tremendous amount of grade points and a lot of data, a lot of analysis, which is also quite in depth. Let me see. I think I have already seen some comment from the audience. That's from Professor Andrew Higgins. Andrew, would you like to ask a question directly?
Sure, yes. I was a little concerned by a statement that was made in the first sentence of your talk, which was that a detonative combustion in an RDE will result in an increase in total pressure. Total pressure, if you're using the term to mean the stagnation pressure of a flow, does not increase through a detonation wave. In fact, a detonation wave is a very large generator of entropy and decreases total or stagnation pressure. In fact, total pressure varies inversely with entropy generation in a flow. So I'd like to understand what you meant when you said that using a detonation will result in an increase in total pressure.
Well, no, this is no. Thank you very much for your question. Well, I was quite sure that if we have a detonation wave or a shock wave in a fixed frame relative to the shock, we have a total pressure loss. But if we are considering a total pressure, sorry, the shock which is in a laboratory frame, so we are not solidal to the reference frame of the shock, we should see a local increase of total pressure. This was my.
Okay, so you're doing it in a laboratory fixed frame, yeah, where the detonation goes past you.
Yeah, that's the difference.
Yeah, I don't even know if it's meaningful to talk about concepts of total pressure in a transient flow like that. So usually when you want to talk about concepts of total pressure, it's only meaningful to do that in a steady or quasi-steady environment. You know, just think about a shock wave, and a shock wave goes by you. Yes, there's an increase in pressure and an increase in velocity. So if you compute the stagnation properties, I guess it would increase, but you have to be very careful with the interpretation of that. A fundamental thing in thermodynamics is total pressure is an inverse measurement of entropy. So from that reasoning, a shock wave would be a very magical wave. It would be a wave that will go by and spontaneously decreases the thermodynamic entropy, which would violate the second law of thermodynamics. So I would maybe caution you from starting your talk with a sentence that implies you found a way to violate the second law of thermodynamics.
Okay, thank you. No, it was just to give a background of what we mean when we say pressure gain combustion. Just only this one. But I agree with you that it's really depending on the not only on the frame but also on the entropy.
Yeah. Okay. Thank you, Andrew, for your comment. I guess this is quite important conceptual statement, like in this whole community of a pressure gain combustion. And yeah, I believe it's good that we make this idea straight and clear to the community. Yeah. Any other questions from the audience? Well, actually, in the meantime, I have a question relatively high level, but I guess this must be something has been already discussed within the Inspire or other RDE developing community. I'm just wondering what would be the way out for this dilemma between more and more complex geometry of the injectors and the total pressure loss, because you want to enhance mixing by making these injectors more intricate or smaller, but I guess this complex geometry introduce the pressure loss from the plenum to the to eventually the pressure in your chamber. So I was wondering, like, what would be the way out? Well, could there be any optimized plan to solve this problem?
Of course, there are, as I shown here, a lot of different configuration of the injection. One of the most, I would say, used, especially in the USA, is the AFRL detonation combustor, which is represented here. We has radially outward injector of the oxidizer and the axial injection of the fuel. And but it is used for, of course, as I know, propulsion of rockets. So until they have a higher impulse than conventional rockets, they still have the gain they need. As far as I know, we still don't have the famous pressure gain inside these devices. But also, in my understanding, it was because we don't know how to characterize the pressure gain of the such unsteady flow at the outlet. So this is, of course, a part which should be clarified when we think about integration to the turbine, because the turbine wants to have mostly, I don't want to say steady, but stay as soon as stable as possible flow, which is pressurized. So a very high speed flow is not, of course, optimized for the wave. It's concerning to your question, I don't know really what will be the future for the real win of the injection system, because still there are many design in different groups which are using all these strategies that you see here. And I don't have here now already a comparison of the pressure losses of all these systems. But of course, I think this is one of the most used in this moment. But also this scheme here is allowing reduced losses, because the flow is injected the oxidizer, which is the most important. It's injected axially, and the axial injection is allowing reduction of total pressure losses across the combustor.
Okay. Thank you for your answer. I believe this is not very easy answer, easy